Um, all right, guys. I hope you're well. I hope you can hear me. We are going to begin today's revision. We are beginning from, I hope you can see my slides. We are beginning from nucleophilic substitution reactions. Let me just go. Yes. We're going to look at SN2, and then we look at SN1, and then we'll just track along like that. We can't do everything very in depth because I think even if you remember those reactions, it takes a lot of time. The arrows, there are many examples. So, and because we want to cover quite a lot today, including benzene derivatives and other things, we'll just learn the main concept on how these reactions go, and then in your own time, go and look at the examples. The good thing with ED, they have lots of questions that you can do for practice. So once we just understand the basic principle on how these reactions work, you can take the examples that she gives and try, push the arrows, determine the products, and see if you understand. And then, of course, you'll know where you can read a bit more, find extra information so that, of course, we know how to do these things. When we checked the papers, there were some questions of these reactions, and it's within the guidelines for what is supposed to be read in terms of good exams. So, yeah, I think we will benefit from this. So I think let's just begin. So nucleophilic substitution reactions, usually a substitution reaction occurs when there's a suitable electrophile and it's treated with a nucleophile. So like you can see in this example here, a nucleophile usually has a pair of lone electrons, which is usually used to attack this electrophile and then form a new bond, and then we have a leaving group exiting the reaction. So like you can see in this reaction, you may not be able to see the arrows, but you can see this electrophile, which is the substrate. We actually call it the substrate more, reacted with this nucleophile. So this minus sign signifies a lone pair of electrons. It attacks here, then you can see it forms a bond, and this chlorine group exits as a leaving group. And then you can see it here as a free fluoride ion. So the term substrate is usually used when you're referring to the electrophile, like we have said, and the substrate involved in a substitution reaction must contain this, a leaving group, capable of separating from the substrate. Next slide. Okay, so that's some of the functions of a leaving group. Usually it withdraws electron density, their induction. So the adjacent carbon, like this one, the adjacent carbon is usually electrophilic. Then it stabilizes any negative charge that may develop as the result of the leaving group separating from the substrate. So some of the common leaving groups that you'll be able to see are the halogens, chlorine, bromine, iodine, and fluorine, and others. So we are going to now begin by looking at the two possible substitution reactions, which is SN2 and SN1. Okay, so for SN2 reaction, if you remember this mechanism, usually the rate of the reaction is dependent on two factors, hence the term SN2. It's dependent on the substrate and also the nucleophile. So the rate equation is usually described as second order. Yes, so the rate of the reaction is dependent on substrate and nucleophile, and that's why it's described as second order. It's linearly dependent on the concentration of two different compounds. So the mechanism usually exhibits a step in which the substrate and the nucleophile collide with each other. So it's a bimolecular step. Two steps occur at once. So SN2 means substitution, S for substitution, and nucleophilic to bimolecular step. So here is an illustration of how SN2 occurs. You can see we have our nucleophile here, which we said examples of nucleophiles are the halogens like bromine, iodine, etc., and the rest. So the nucleophile attacks the electrophile of the substrate which contains the leaving group. So it's one mechanistic step. The attack of the nucleophile and the exit of the leaving group occurs in one bimolecular step. So that's exactly what you can see here. Nucleophile attacking, and you can see it's very crucial to note that it's attacking from the back. Usually in SN2, it's a backside attack. So you can see the nucleophile attacking here, and then the leaving group exiting, and you have the free leaving group, and this new compound with the attached nucleophile. Okay, so stereospecificity of SN2. What happens is when the position is a chirality center, I'm sure you remember that from the discussion that we had on Monday, a change in configuration is observed. So for example, we have this compound here, its configuration is S, and then we have this is the nucleophile. So as you can see, there's a new compound here after the SN2 reaction has taken place, and this bromine is the leaving group. It has exited. This SH has attacked, a nucleophilic attack. So what you can tell is, or what you can see on this side is, this compound has a different configuration as compared to this. So the reaction is therefore said to proceed with inversion of configuration, also known as Walden inversion. So the requirement for inversion is what we've just said, at an attack from the back side and never from the front side. So when the nucleophile attacks, it attacks from the back, which causes that thing we talked about, like an umbrella flipping in the wind. So the nucleophile attacks with simultaneous loss of the leaving group, which causes the chirality center to behave like an umbrella flipping in the wind. You can just picture an open umbrella. If you have an open umbrella and it's attacked from like the inside, or like when it's a rainy day, then your umbrella overturns. So that's exactly what happens, an umbrella flipping in the wind. So you have an inversion of configuration. So if your reactant is S configuration, the configuration of your product will be R. Yeah. So SN2 reactions are usually said to be stereospecific because the configuration of the product is dependent on the configuration of the starting material, which is what we've said. If you've started with R and it's proceeding with SN2, you will end up with S. So, so for example, here we have bromobutane is a substrate and hydroxide is the nucleophile. So in this case, the position is a chirality center, so there will be an inversion. So draw an arrow pushing mechanism for this reaction. So what will happen here, you can see this is the nucleophile. It has this negative charge, which means there's a lone pair. So this nucleophile, I don't know how to draw, so just follow my cursor so that we can see what happens. So basically this nucleophile will have an attack here to this carbon here, which contains a leaving group. And then simultaneously, this bromine will exit. So it's because it's the leaving group. So you end up with this OH attaching to this carbon, as you can see here. And then the bromine exits as a leaving group, as you can see here. Two simultaneous steps in one reaction. So that's SN2. So for these examples, like we said, if you just do what we've explained here, the two reactions, you'll be able to know how to draw the product for each of these. For each of these, with this being the substrate, this being the nucleophile, then you'll be able to see the products of each of those reactions. So, okay, this is an exercise that is part of this SN2. So it's a little bit of a longish question. I will not say that I drew the material and the product of inversion, but they are saying that, in this question, that the reactant, okay, let's just read. When S1-bromo-1-fluoroethane reacts with sodium methoxide, an SN2 reaction takes place in which the bromine atom is replaced by a methoxy group. So the product of this reaction is S1-fluoro-1-methoxyethane. So how can it be that the static material and the product have the S configuration? So draw the static material and the product of inversion and explain the anomaly. So this question is talking about an exception to the rule where an inversion always occurs when you have an SN2 reaction proceeding. I tried to do some extra research and see, and the only thing I could find is that configuration is maintained when instead of a backside attack, the nucleophile attacks from a front side attack, so there will not be inversion of configuration. So that's the only thing I could figure out as to why the reactant and the product is S. But if anybody is able to search and find something else to add, because I felt like maybe that's not sufficient to understand why this reactant and product have retained configuration, you can just tell us. Yeah, if you search and you find any other reason, you can just tell us so that we understand why this specific one is an exception to the rule of inversion. Yes, so that's that for SN2. So the rate is usually sensitive to the nature of the starting substrate. We have the least reactive being tertiary substrates, most reactive being methyl substrates. You can see how the reaction proceeds. And we can see here below, steric hindrance affects the reaction rate. So,
Sonia?
Yeah.
For that question, you said the reason for not, like, there's no inversion is because, sorry, I missed that part.
Oh, this question here.
Yeah.
The reason I was searching online on I think the ChemLibre website, and they were explaining about the only time an inversion does not occur is when there's a front side attack. Because we've said with SN2, it's always backside. That's why you have the inversion of the configuration from like R to S or S to R. So it was just saying if there's a front side attack is when the configuration will be retained. But I was feeling like when I read that whole paragraph, I was not feeling like that's sufficient to explain, because why would this specific reactant undergo front side attack, yet we say SN2 always proceeds by backside, which is why I put the disclaimer. If anybody can find any extra information to help us understand why this specific reaction results with an S in the reactant and an S also in the product, you can just share with us so that we can have a deeper understanding. But
Okay.
Yes?
Yeah, so I had seen a similar example, or I don't know. So apparently, because it doesn't change configuration, because
Yeah.
the priority of the groups, they change. So they're not the same priority as your reactant. The priorities change around the group because you're adding a methoxy group, which has a higher priority compared to now like the fluorine, which had second priority in the product. I think
Oh,
something like that, yeah, because
yeah.
priorities change. So when the priority changes, that's when like the configuration stays the same, but I'm not too sure. I had seen something like that.
When priorities change. Oh,
Yeah.
because this molecule is 1-bromo, 1-fluoro. So the living group in this case is bromo. Yeah, because the product will be 1-fluoro, 1-methoxyethane. Okay. Okay. I think I can see it. Thank you for that, Hiral. I think I'll also just try to draw it, and all of us can just try to draw it out and see how the structure looks and how the will be able to understand. Thank you so much, Hiral. Okay, so what were we? Where were we? We were talking about hindrance affecting the rate of the reaction. So for SN2 reactions, because we said usually when the nucleophile is attacking, it's a backside attack. When you have these groups, you see this like a tertiary substrate, it has these 3 methyl groups. That crowding usually hinders the attack of the nucleophile, which is trying to attack that carbon which contains the leaving group, so that the leaving group can break off. So the bigger the groups, the bulkier the groups, because of course we know CH3 is much more bulkier than a hydrogen, the more the steric hindrance, and therefore the slower the reaction, because backside attack of the substrate is is prevented. It's very hindered by bulky groups surrounding the living group. So that's what explains the rate of the reaction when it comes to looking at the nature of the starting substrate. The methyl substrate much faster because hindrance is much less compared to a tertiary substrate. It goes rate goes decreasing when you move from methyl to tertiary substrates. Okay. This is basically just explaining what we've talked about. The activation energy for the reaction to occur will be higher, which activation is just the energy required for a chemical reaction to take place. So the more activation energy required, the slower the reaction. So you'll see for a tertiary substrate, it will require the most activation energy for this SN2 to take place. All right. So we can look at SN2 with alcohols. So primary and secondary alcohols usually undergo substitution with a variety of reagents which can proceed via SN2. However, OH is a very poor living group. So it must, before carrying out a substitution, it must be converted to a good living group. OH is usually a good nucleophile. It's very good for attacking, but it's not a good living group. So if you want if we want it to function as a living group, we must protonate the OH, which will automatically become water. Of course, if you protonate an OH, it becomes water, and water is a neutral molecule and hence a very good living group. So we can take a look at this reaction here. So primary alcohols will react with HBr, hydrogen bromide, by an SN2 process. So you can see this which is a living group OH, picks this proton and then it forms water. You can see here. And then this leaves an extra pair of electrons on the bromine, hence the negative charge. And because we've used one of these protons here to form the bond with hydrogen, we have this positive. Addition of like one pair of electrons. Then we have the formation of this, and water, our living group, exits very simply. So we can see this bimolecular step occurring here. So for SN2 reactions with alcohols, this reaction works well, but works well for HBr, but does not work well for HCl. So to replace the hydroxyl group with chloride, zinc chloride is used as a catalyst. This is just a different way the same reaction can occur. If you're not using hydrogen bromide, you can use zinc chloride because the one with hydrochloride does not work as well. So the catalyst is a Lewis acid that converts the hydroxyl group into a beta living group. The goal here is to just make the hydroxyl group into a beta living group so that you can have your SN2 reaction taking place. All right. This is another option of the alcohol being converted into a tosylate, and then you proceed with a nucleophilic attack. And then this is also another option. If we could read through all the slides, we would, but we need to move because there are so many reactions happening. So I think we've understood basically how SN2 works. These are just extra slides for us to understand a bit more. Because we have quite a number of reaction mechanisms to look through, unless there's a question on just how SN2 works generally, I think we can proceed to SN1, but we can move to the others, E1, E2, and the rest of the videocasts. So please, if anybody has a question or anything to interrupt, just feel free to unmute and ask because I can't see the screen. I'm just seeing the notes, so I'm just proceeding with the notes. So I think we can get into SN1, the SN1 mechanism. Okay, just a second. Okay, so for SN1 is usually a stepwise process in which there is, first of all, there's loss of the living group to form a carbon cation intermediate, followed by nucleophilic attack on the carbocation intermediate. So we said in SN2, the steps occur simultaneously. In SN1, they don't occur simultaneously. The first step is usually the loss of the leaving group, and then once you've lost a leaving group, we have the intermediate carbocation. So carbocation is very, very key in SN1 mechanism of reaction. Then now we have nucleophilic attack of the carbocation to form the final product. So the names, we said SN2 depends on the concentration of both the substrate and the nucleophile. This one only depends on the concentration of the substrate. So increasing or decreasing the concentration of the nucleophile has no measurable effect on the rate, and it's first order. It's a first order reaction. So the rate determining step usually involves one chemical entity. And the mechanism is said to be unimolecular. So substitution, nucleophilic, unimolecular. So here is an example of a reaction mechanism. So a question, what happens to the rate if the concentration of tert-butyl iodide is doubled and the concentration of the sodium chloride is tripled? So tert-butyl is this one. Of course, this is the substrate, and then sodium chloride is our nucleophile. And we've said this one is only dependent on the rate of the substrate. So for A, if we double the rate of our substrate, I believe that the reaction rate is going to double because SN1 is dependent on substrate. The second question asks if the concentration of tert-butyl remains the same and the concentration of sodium chloride is doubled. So if this remains the same, which is what is dependent for SN1, and this is doubled, it will have no impact on the rate of the reaction because we can see the concentration of the nucleophile has no measurable effect on the rate. So yes. So here is so this one is not different from SN2. The tertiary substrates are most reactive, and the order of reactivity changes. The more substituted the carbon is, the more reactive in terms of SN1. Excuse me. So the trend is opposite of what is observed in SN2. So for the structure of the substrate, the rate is usually dependent on how quickly the leaving group leaves to form a carbocation. For SN1, that's the key factor, the formation of the carbocation. Here, steric hindrance is not at play because the rate determining step is not about the nucleophilic attack like it was in SN2. So the dominant factor is now carbocation stability. So as you can see here, carbocations are stabilized by neighboring alkyl groups. So this tri-substituted carbocation is the most stable compared to this one, which just contains this primary substitution of secondary or even this one that has hydrogen. This is the most stable, hence why tertiary substrates are have a faster rate of reaction in SN1 because they form the most stable carbocation. So this is basically just explaining what we have talked about in terms of activation energies. Forming a tertiary carbocation will have a smaller activation energy than formation of a secondary. And hence tertiary will move at a much faster rate in terms of reaction speed because the activation energy required for the chemical reaction is lower. So yeah, so I think that's important to note. So we can take a look at an example real fast. So draw the carbocation intermediate of the following SN1. Here we have, here's our substrate, here's our nucleophile. So as you can see, here is let's just look at the solution. It's helpful to draw the curved arrows. They're used to push arrows to see. So once this leaving group leaves, because that's the first step in SN1, once the leaving group leaves, you have formation of this carbocation. So like you can see this one, the leaving group, this chloride group has left. We have this tertiary carbocation, which is the most stable carbocation, and the chloride, which the chloride group which has left. Here's just to note, carbocation has trigonal planar geometry. So the then what would happen is, I can see it's not in the other slide. This once this group has left and we have this carbocation, this our nucleophile will now attack right here, like you can picture that arrow till like here, and then you'll have formation of this final compound, because now this attacks this compound here with the carbocation, and you have your final. Okay. So this is just examples for you to practice. If, for example, we are using this same nucleophile for this one, it will, what is the first step? Loss of the leaving group. So the bromine exits, then this will form that carbocation we're talking about, a tertiary carbocation, the positive ion. I hope you can envision it, will be somewhere here. Then our nucleophile would attack right here where the carbocation is, and the group will attach here by formation of a new bond, and you will have you. We can do the exact same thing for the others, and you'll be able to see what happens there. So here there's a question that I also had to research a bit more. Just a second. So identify which of the following substrates will undergo an SN1 reaction more rapidly. Explain your choice. So we can see the exact molecule except one is a benzene, the other is just it doesn't have that aromaticity. So I was able to see this one. This one will undergo a reaction more rapidly due to the delocalization of these pi electrons, these pi bonds. So I wanted to read something. The reason that the positive charge can be localized. Yes. So let me just find it on my here. Just a second. Because the one I've taken on my phone is not so clear. Yes. So for these compounds which are contain pi bonds, in molecules in which the carbon next to the site of substitution contains a double bond, SN1 reaction is possible. The reason is that the positive charge on the carbocation can be delocalized among multiple possible resonance structures, making the carbocation dramatically more stable. Yes, that's just all I want. So the carbocation in this structure that contains a benzene ring, let me share my screen. Is much more stable because of the delocalized pi electrons in that structure. So it's the one which is more likely to undergo SN1 reaction in comparison to the other one. Here it is. Yes. So I think okay. Sorry about that. So I think we can understand why this would undergo an SN1 reaction more rapidly. So yes, so for stereochemistry for SN1, SN1 usually involves of course, the intermediate carbocation, which we have said a lot. It can be attacked from either back or front, leading to both either inversion of configuration or retention of configuration. And so because either can happen, because it's planar, the reaction usually produces a racemic mixture of enantiomers. However, there's usually a slight preference for the inversion product. So of the products, you'll have the inversion product being slightly more than 50, the retention being slightly less than 50. So an arrow pushing mechanism, I think we now know how this will happen. This leaving group leaves, you have the formation of the carbocation, and then the nucleophile attacks, and you have your new group, like you can see here, nucleophilic attack to this carbocation, and you have the bromine, the new compound here. Yes, This is the same thing. We will do practice a bit later. So for preparation of alcohols via SN1, alcohols usually are prepared by substitution reactions in which the leaving group is replaced by a hydroxyl group. So you can see here, there's a tertiary group, and water here is our nucleophile. So we have the SN1 reaction of this leaving being protonated by this water and then forming this hydrochloric acid and this final product. So like we said before, I think we mentioned it, I think during SN2, that hydroxide is a very bad living group. It won't live by itself. So for you to convert this, for it to leave the substrate, you must protonate it. Hence, you require acidified conditions for you to convert OH into a good living group. So you can see here, acidic conditions are required to allow SN1 reaction. Instead of just water, you can, like in an acidified medium, this water is protonated. So this OH will pick this proton and then form water. Here it is. Then water breaks off very easily, leaving a stable carbocation, which now undergoes attack. Then you have your final. So the two core steps of this SN1 are, first of all, you proceed with a proton transfer. That's if OH is your leaving group. So this is pretty much the same thing. I think we can note about solvolysis. So reactions in which the solvent functions as a nucleophile, these reactions are called solvolysis. So I think this is an important concept to mention. So let's just jump here. For carbocation, you can have rearrangements during an SN1 process, because what drives SN1 is the most stable carbocation. So if you look at this example here, carbocations are susceptible to rearrangement via either a hydride shift or a methyl shift. So look at this substrate here. We have the bromine leaving group, it leaves, but you can see here it has formed a secondary carbocation. But there are two methyl groups here on this beta carbon. So what happens is it will experience a methyl shift. This group here will break off, come here and form a bond here. And of course, as a result of this bond breaking, the carbocation will shift from this position to here. And here we have a more stable tertiary carbocation. So the nucleophilic attack will happen here and the chloride will attach at this point, not here. If you can see the reactant here, the substrate I mean here, the bromine was here, but the final chloride did not attach here because there was a methyl shift to ensure stability of the carbocation. So usually the same thing happens with a hydrogen can shift to just ensure that the carbocation that you're working with is the most stable form of carbocation for the nucleophile. I hope that is clear. So in reactions where a carbocation rearrangement is possible, a mixture of products is obtained. Like you can see here. Like this is the exact product that we had here. You can see this is the same as this. So they're saying a mixture of products is obtained. The product we should obtain if the secondary carbocation did not undergo a methyl shift. This is the product that will be obtained. Then this is the product that is obtained after the methyl shift occurs. Yes. So yeah, so this is just an exercise. We can just do one and move on. So for each of the following substrates, determine whether an SN1 process is likely to involve a carbocation rearrangement or not. So if we look at A, for example, whatever group here leaves, like if this group leaves, there will be no carbocation shift because you will have a tertiary carbocation forming. If we look at B, the OH group here is the leaving group. If this leaving group exits, and then we'll have the formation of a secondary carbocation. Here we will definitely have a carbocation rearrangement because we will be able to have a methyl shift from these two methyl groups here. One methyl group will shift here, and then the carbocation position will be here, forming a tertiary carbocation, which will be the most stable form of carbocation for attack by a nucleophile. So I think those are enough examples. Yeah, we are done with SN1 and SN2 reactions. There are so many organic reaction mechanisms. So for these subsequent ones, because which is about 8:30, we want to now look at the other aspects of chem. We'll just stop. So I'll just go through high level, just forgive me if I'm rushing a bit because there's so much. At the end of the day, we're just going to have to read to understand for ourselves. So here we'll just be going juju, and then we proceed with the Jasmila's part from 8:30, and then we look at a few questions from the past papers. So let's just look at electrophilic aromatic substitution. So while alkenes usually undergo addition reaction when benzene is inert under the same conditions. So the inertness of benzene, like you can see here, we talked about the localized electrons when we're talking about that the thing that I just read. And the reason why this will undergo an addition reaction very easily and this benzene is inert is because benzene is so stable because of those delocalized pi electrons. So it does not want to alter that stability by reacting with other molecules like bromine, for example. So it needs an extra boost for it to be able to react with bromine and form these products, unlike alkene. These delocalized pi electrons greatly contribute to the stability, hence causing it not to, let's use the word desire, for lack of a better word, desire to undergo other forms of reactions because of stability. So when iron is introduced into the mixture, a reaction takes place, and rather than addition, an electrophilic aromatic substitution is now what takes benzene. So you can see benzene here reacting with bromine in the presence of iron results in this electrophilic aromatic substitution. So this is the same thing that happens with chlorine, and you can see all this this moieties here when they react with benzene, addition reaction, but rather an electrophilic aromatic substitution. So we can see halogenation here. Can begin here briefly. So chlorination of benzene is usually accomplished with a suitable Lewis acid, such as aluminium trichloride. You can see here. So this is the one which sort of like catalyzes the reaction because it will not react with chlorine alone. So what you can see here is chlorine, Cl2, this one, reacting with this aluminum chloride to form this complex here, which reacts as if it were chloride positive, not the one that we usually know. So we can just take a look at this reaction because it's similar for bromine. So once we look at this one, we won't look very in-depth into the other ones. So you can see the first step here for us to have the electrophilic substitution of this benzene reacting with the chloride. We are having this chloride reacting with aluminum chloride, forming this complex. Then our benzene molecule here, what is it called? This pi bond here, these two pi electrons are what are used for nucleophilic attack. So this benzene is the nucleophile. This here is serving as our substitute of our electrophile. So this pi bond here picks this chlorine, and then you can see the beginning of the sigma complex. You can see this pi bond picks this, then the chlorine. It forms the bond here, and then we have broken this double bond here because this bond has been used to form this bond here with chlorine. Then now we have the delocalization of the electrons. We have, because this bond has broken, we have a deficiency here. So we have the movement of these electrons, which now shifts the carbocation, the secondary carbocation here, and that proceeds again. Now we have this pi bond moving here, and the carbocation coming here. And then now we have the breaking of this this bond here with the hydrogen. This complex here that we had formed here is what picks this proton, and then that's what breaks this bond, restoring aromaticity in this compound. So the benzene is, the aromaticity is restored, and we have the chloride now attached. So we've achieved the halogenation of the compound. If you follow the arrows very carefully, you'll be able to see clearly. I think it explains fairly clearly how we begin the picking of these electrons, and then the sigma complex. In this complex is where the aromaticity is broken, but it's restored at the end here by the picking of this proton by this complex, and the final product with aluminum chloride and hydrochloric acid. So that's what happens for halogenation. The same thing happens for bromination. It's literally the same exact reaction scheme. The only difference, it's not aluminum chloride. We use iron bromide, iron tribromide, as you can see here, which is a Lewis acid. Yes, so in the first step, the aromatic moiety is the nucleophile, like we have said. That pi bond is what attacks the electrophilic, which generates the positively charged intermediate, which is a sigma complex. Excuse me. That is resonance stabilized. Then in the second step, the sigma complex is deprotonated, which restores aromaticity, regenerating the Lewis acid. And that's basically how the halogenation of benzene. For halogenation, for chlorination and bromination, it's much easier. Chlorination is a very violent process, as you can see in this large point, and it's difficult to control, while iodination is often too slow. So there is very poor yield. That's just basically going down in the group 7 of the periodic table. Chlorination is very violent, very fast, then it goes like that until iodination is too slow with very poor yield. So an example is of the drugs that we know. So for example, a chlorine atom is installed in the para position of one of the phenyramine rings. You have a new product called chlorpheniramine, which is 10 times more potent. The same concept with bromine atom being installed. You have brompheniramine. Yes. So for sulfonation, sorry, I'm sorry about that. Oh. Just a second. So for sulfonation, benzene is usually treated with fuming sulfuric acid. Then the sulfonation process happens. So we just probably need to know this catalyst for the reaction, resulting in benzene sulfonic acid. So this is the mechanism, very similar to the mechanisms that we've seen for chlorination and for bromination. The pi bond picking, undergoing nucleophilic attack to the electrophile, and then we have the sigma complex and the regeneration of aromaticity resulting in our product. Nitration is similar. The difference is now we look at the catalyst for the reaction. You have nitric acid, and also a mixture of nitric and sulfuric acid results in the nitration, which occurs in which nitrobenzene is the end product. Here you have the formation of the nitronium ion, this one right here from this mixture of nitric and sulfuric acid, which causes the reaction to proceed. Yes, so usually the nitro group can also be reduced to give an amino group. In this process, as you can see, is catalyzed here. This usually provides a two-step method for installing an amino group on the aromatic ring. Nitration followed by reduction of the nitro group. Those are the two steps that occur. So that's just an example for us to draw the mechanism of reaction. Here we have Friedel-Crafts, alkylation. So basically, Friedel-Crafts in summary is installation of an alkyl group on an aromatic ring. We've talked about halogenation, like trying to install chlorine, installing bromine, installing these nitro groups and the rest. For Friedel-Crafts alkylation, we are installing an alkyl group on the aromatic ring. So like you can see here, this is the benzene, this is the substrate, and this is the product. That's the result of alkylation. So usually it's also in the presence of a Lewis acid. This group here, usually chlorine is a sufficient enough leaving group, but when you're doing Friedel-Crafts, it's not electrophilic enough to react with benzene because of the stability of benzene. So we usually incorporate aluminum chloride so that's why we are saying in the presence of a Lewis acid such as aluminum trichloride, the alkyl halide, which is this one, is converted into the carbocation, which is now what attaches to the benzene to now cause the attachment to the installation of the alkyl. So if you look at Friedel-Crafts, here you begin with the reaction of this alkyl halide with aluminum trichloride. You have the formation of this carbocation. This carbocation is what undergoes nucleophilic attack by our benzene. What we've established is that benzene is the one which always attacks our, like whether it's the halogen or whatever, it's one which attacks to form the product. So benzene, nucleophilic attack of the carbocation, then it's again the sigma complex, it picks the proton, and you have now here your final product, alkylation. So yes, so we proceed. Secondary and tertiary alkyl halides are readily converted into carbocations in the presence of aluminum chloride. So this is just to remind us, carbocations usually undergo rearrangement, like we spoke about, I think, in SN1, to the most stable form of the carbocation. So here is where we get to see a hydride shift. So one chlorobutane here is treated with aluminum trichloride. Of course, this group leaves. Then a hydride shift occurs. This hydrogen here shifts here so that the carbocation can come here to form a more stable secondary carbocation instead of having the carbocation here at the end. So what happens is if there's that shift, you will have the mixture of products being obtained after alkylation, the attachment of the alkyl group to the benzene. So here you have 35% of this product, the least stable carbocation, and this one, which would be the most stable carbocation, will be the more abundant product. There are some limitations of Friedel-Crafts alkylation. So the carbon atom usually connected to the halogen must be sp3 hybridized. So vinyl carbocations and aryl are not stable enough. So you can see this one. sp3 hybridized is usually alkane. So, because this one is sp2, alkene, anywhere where there's a double bond, it's usually sp2 hybridized, and alkyne, we say this sp hybridized. So if the substrate has a double bond, this reaction is not going to proceed. Even if you have the presence of aluminum chloride, it's very important to note this. Friedel-Crafts takes place only if here the substrate is sp3 hybridized. So, like if you remove this double bond and we just have this this substrate, then the reaction will take place. So also something to note is installation of an alkyl group usually activates the ring towards further alkylation. So once the first alkylation has occurred, the ring is now more sensitive towards further alkylation, which we are calling polyalkylation. So once you've attached this one, you can see it has repeated, and there's still another butyl group attached to the benzene ring. Certain groups, such as nitro group, are completely incompatible with Friedel-Crafts. So if you have this benzene which is substituted here with this, it will not happen because of the deactivating groups. You'll be able to see that briefly in the next section. So yeah, I think that's about it. With Friedel-Crafts alkylation, it's just the same thing. The leaving group leaves, and then you have attachment of whatever alkyl group is there. It attaches to the primary reactant, and you've achieved your alkylation. So for Friedel-Crafts acylation, it can be used to install an acyl group. So here is an alkyl group. Here is what we are referring to, an acyl group. And the reaction that installs an acyl group is called an acylation. So this is like moiety. So usually acyl chloride is treated with a Lewis acid to form a cationic species called an acylium ion. So here is our Lewis acid, aluminium chloride, and here is it's being treated with this group, and you form your acylium ion. This acylium ion is resonance stabilized because of this these lone pairs of electrons, these free these free electrons, so they are therefore not susceptible to rearrangement. So here is the reaction scheme, very similar to the ones that we've seen before. The initial reaction is aluminium chloride, then the generation of the acylium ion. You look at the nucleophilic attack, the sigma complex, and your final product after deprotonation. And now here is your final product. So there are two main steps. The acylium ion is attacked by the benzene ring to produce the intermediate sigma. Then the sigma is deprotonated to restore aromaticity. So what happens is the product of acylation is an aryl ketone. It's not what we are doing is we are trying to result with an alkylated reactant, but the product of acylation is an aryl ketone, which can be reduced using a Clemmensen reduction. So this is how your product for Friedel-Crafts acylation look like. It won't be an alkyl group. So now what you're saying is you can reduce it by a Clemmensen reduction to result in, the net result is now the installation of an alkyl group, which is what we are aiming at with Friedel-Crafts, installation of an alkyl group. So once you have this, you undergo Clemmensen, zinc, or mercury in the presence of hydrochloric acid, and you have your product. So yes, this two-step process is a convenient synthetic method for installing alkyl groups that cannot be efficiently installed with a direct alkylation process as a result of rearrangements. Okay, so I feel like we have looked at so many what is it called? Organic reaction mechanisms. I wanted us to look at E1, E2, but I think time is gone. So some of these reactions, we can't, like I said, we can't cover all of them here. Where is that E1, E2? In one of the questions that I saw in the paper, they were talking about, there's a question on aldol condensation. So maybe I can just touch on that one. But we can't really be 100% sure which reaction will come. So it's good for us to know all of them. But let me just touch on the aldol. And even this Markovnikov addition was also in one of the past papers. So just so that at least by 8:30 we are done with, we've done what we can with organic reactions, organic reaction mechanisms. The ones that we've not covered together, we can just everybody can just read on their own, because we definitely can't do all of them together. So let me just look at aldol reactions a bit, because when we go through the questions, we'll be able to see a question on this. If we have time at the end, we can look at E1 and E2 briefly. If not, again, tutasoma tu. So aldol reactions is still one of the organic reactions, organic reaction mechanisms. Is this the first slide regarding? Yes, it is. So basically, you can see we have a ketone. What we are starting by doing is recalling when an aldehyde or ketone is treated with sodium hydroxide, both the aldehyde and the enolate will be present at equilibrium. So under such conditions, a reaction can occur between these two species. So yes, so here we are. So treatment of acetaldehyde with sodium 3 sodium hydroxide gives 3-hydroxybutanol. So this is, of course, this is the structure of acetaldehyde. We're looking at it being reacted with sodium hydroxide, and this is the product. This is our product, 3-hydroxybutanol here, the same as beta-hydroxybutanol. So the product exhibits both an aldehydic group and a hydroxylic group, and is therefore called an aldol, because we have this aldehyde group and this OH group. So of course, aldol, ald for aldehyde, ol for alcohol, and this reaction is an aldol addition reaction. The product of this aldol addition is always a beta hydroxyaldehyde, beta position. This being alpha beta, so beta hydroxyaldehyde. This is the arrow pushing mechanism for how this reaction takes place and how it's formed. I think we can be able to, because most of our exams is MCQs, so we will not be asked arrows, but to understand how the product is formed is important. So you can just take a look at this. Reaction scheme, it's short, it's pretty very straightforward. So for most simple aldehydes, the position of equilibrium favors the aldol product. For this is simple aldehydes, just like a basic aldehyde, the equilibrium will favor this product, the aldol product, the one which contains the one which contains the alcohol and the aldehyde. But for most ketones, the aldol product is not favored, and poor yields are common. So you can see when you're reacting a ketone, in the same reaction condition, sodium hydroxide and water, it's only 20% of the product, the aldol product, that is formed. But for aldehyde, 75% is formed. So simple aldehyde, the position of equilibrium favors the formation of this aldol. So this is a reaction, aldol addition reaction. I think these things would really work if in a place where we had a whiteboard to push the arrows, but you can just figure out how to draw this mechanism of reaction. You can use this as a guide because it's saying reacted with sodium hydroxide. So this is the exact same thing, hydroxide reacting with this aldehyde. You'll be able to form the products. Actually, here it is. So OH reacting at this point, formation of the this intermediate, and then we have this attack, and we have the formation of our final product. So there's 3 mechanistic steps: 1, deprotonation, then nucleophilic attack by our nucleophile, and then finally protonation, and the result of a beta hydroxyaldehyde. So the question was actually on aldol condensation. An aldol addition reaction will undergo elimination when heated in these acidic or basic conditions to produce unsaturation between the alpha and the beta positions. So now we've started with aldol addition so that we can come and look at aldol condensation. So the product of this aldol addition is what undergoes elimination. Okay. when heated in acidic or basic conditions to produce unsaturation between the alpha and beta positions. I think this would be really nice if I had already spoken about E1 and E2, because for elimination reactions, what happens is that the proton, like you can see this to this, the proton is picked. Unlike substitution reactions, this proton is picked, and then once this once this proton is removed, you have the formation of a double bond here between the alpha and the beta positions. So E1 and E2 works in a very similar fashion as to how we are seeing this aldol condensation working. You can see this OH group has been deprotonated, like we saw the 3 mechanistic steps: deprotonation, nucleophilic attack, and then protonation. So this group is deprotonated. Once you pick this proton, it's left with an extra pair of electrons, which is a extra pair of pi electrons, which come here to form a double bond between alpha and beta, and this is usually your product as a result of an aldol condensation. So this transformation is most readily achieved when aldol addition is performed at elevated temperature. So aldol addition reaction occurs at a high temperature. You have this aldol condensation occurring with the deprotonation and then the formation of the double bond, and this is usually your product. So it's a two-step process: aldol addition plus dehydration, which is called aldol condensation. So yeah, so you'll see for an aldol condensation to take place, you're reacting two aldehydes, as you can see here, two aldehydes resulting in an aldol addition, beta hydroxyaldehyde. Then the dehydration takes place to form the beta unsaturated aldehyde plus a free. A condensation reaction always results in liberation of a water molecule. So this is just a summary of aldol addition and aldol condensation. You begin by aldol addition, these two, aldehyde plus aldehyde, giving you this beta hydroxyaldehyde. Then at elevated temperature, you can have now this process of this jumping all the way up to the formation of this product, which is the beta unsaturated aldehyde, plus the liberation of water, which is the aldol condensation. So yeah, in cases where two stereoisomeric pi bonds can be formed, the product with fewer steric interactions is generally the major product. So trans isomerism is what is favored. Like you can see here, there is a pi bond and its opposite sides. This group and this group are on opposite sides. So this is the product which will be favored as compared to having both products on the same side of the double bond. So this is what this is saying. In a case where two stereoisomeric pi bonds can be formed, the product with the fewer steric interactions, which is this one, you can see the products are on opposite sides, it will be more favored than the other one. So the driving force for aldol condensation is the formation of a conjugated system, and we achieve aldol condensation by performing the reaction, the aldol addition reaction at an elevated temperature. So, okay. So all this is happening. So this is just basically what we've just mentioned. The one where there's less steric hindrance is the one which will be the product which is more favored. So trans isomerism compared to cis isomerism. We have here the condensation products for each of these. We could have done this, but time is not on our side. So that's basically the aldol condensation. I I have skimmed through it, but time does not allow for us to really go through each and every little detail. But I think the important thing to know is that aldol additions at elevated temperatures result in aldol condensation, and then the product where the trans product is more favored than the one which has more steric hindrance. And the starting reactants for an aldol addition is two aldehydes, formation of the beta hydroxyaldehyde and the beta unsaturated aldehyde. So allow me to just ask Jasmila to just take us through the other part, because it's still a lot for her to take us through. Then we can look at the questions from the previous board exams. You can look at E1 and E2. It's very simple, similar to SN1 and SN2, just withdrawing of a proton, and also the others which we've not been able to look at, like the phenols and the rest. And then if there are any questions, we can always discuss on the group. So Jasmila, I think I can stop sharing so that you can share the other PDF. Actually, it's a PPT. Then you can take us through the other stuff, the other part of this organic chem.
So we can continue. We can continue with heterocyclic compounds. So yesterday we had stopped here, replacement nomenclature. So we can continue from here. So pyridine is a weak base. It's the most important derivatives of pyridine include nicotinic acid and nicotinamide, which are classified as vitamin B, both of them. So these are the two important derivatives of pyridine. We have nicotinic acid and nicotinamide. Yeah. So what else? Pyridine can be converted to pyridinium, which is the ion. Vitamin B6 is the group name for 3 related derivatives of pyridoxine, pyridoxal and pyridoxamine. As seen here, we have pyridoxine, pyridoxal, and pyridoxamine. All of them come from pyridoxine. Pyrimidine, also known as 1,3-diazine, is a dibasic compound. The 3 pyrimidine bases are components of nucleic acids also. So we have cytosine, uracil, and thiamine, and these are their structures. Yeah, so cytosine, uracil, and thiamine. Purine, surely Patrick. Okay, so purine, also known as pyrimidinol. This is the structure. The numbering starts from the main heterocyclic compound. So here the counting starts from this point here, and then we continue. We want this nitrogen to have the lowest numbering, so we go clockwise direction. So we start here 1, 2, 3, all the way till we come back and finish. Then purine bases, we have adenine and guanine as seen here. Then other derivatives of pyrimidine, we have hypoxanthine and xanthine. Xanthine is found in coffee. It's an alkaloid. It's found in coffee. Also uric acid. You're familiar with uric acid, and also these other forms of pyridine. Methylxanthines are N-methyl derivatives of xanthine, also known as alkaloids, as I've already said. So they can be found in coffee, tea, cocoa as well. Alloprenol is an isomer of hypoxanthine. As we are familiar with, alloprenol is used to treat gout. So this is hypoxanthine. It's an isomer because of we see the position of nitrogen in this indole ring. Indole or pyrrole? Pyrrole. Indole. So it's an isomer of hypoxanthine, and we see it's because of the location of this nitrogen. We see this nitrogen here has moved here. So yeah. And also another derivative is mercaptopurine. This drug is used for in cancer treatment as well. So it inhibits the synthesis of purine bases. Then we have pyrrole. Pyrrole, the most important derivatives of pyrrole, we have heme and chlorophyll, and also linear tetrapyrrole. These are bile pigments, yeah. So you can see there's, yeah, so you can just see them there, all of here. All of these are derivatives of pyrrole. Then we come to indole. Indole, also known as benzopyrrole. So tryptophan is a standard amino acid which is biologically active. Is a standard amino acid from which biologically active compounds are derived. So derived, all of these are tryptophan is derived from indole. Yeah. So all of these slides are just showing how the different heterocyclic compounds can be found in different compounds, in different drugs, in different also like in the body, like in heme and everything. Yeah. Then we have serotonin, which is a neurotransmitter, plays a very important role in depression. So we see also the structure, it has the indole ring in it. Also melatonin, we know melatonin is released from the pineal gland and has a role in control of diurnal biorhythms. It is used for treatment of primary sleep disorders. So this is the structure from melatonin. Then another important heterocyclic compound, we have imidazole, also known as 1,3-diazole. So the ion for imidazole is known as imidazolium cation. We see it here. So it's a weak base where one of the nitrogen atoms can add a proton. And then we also have histidine. Histidine is decarboxylated to form histamine. We know histamine is responsible for allergies in the body. So histamine originates by decarboxylation of histidine and acts as a vasodilator in inflammation and allergic reactions as well. So it causes contraction of smooth muscles of the bronchiostem and increases acidic stomach secretion. So yeah. And then another ring, a very important ring, is thiazole. The thiazole ring occurs in thiamine, which is vitamin B1. It also contains the pyrimidine ring. So a fully saturated thiazolidine ring appears in the structure of antibiotics such as penicillin. So here we have the structure of penicillin. We see there's the beta-lactam ring, and then on the other side we have the thiazolidine ring. Yeah. As thiazolidine, we see sulfides here, nitrogen. So yes, and then oxygen-containing 5- and 6-membered rings mostly are very rare. They're very rare, contrary to the tetrahydrofuran. Very rare to find furan, but easy to find tetrahydrofuran. This is tetrahydrofuran. This is furan. So we find tetrahydrofuran in sugars like this D-ribofuranose. I know you're very familiar with this from biochemistry. Then oxygen, okay, still, then we have the 6-membered ring, like pyran. Pyran is a labile ring, but it is stabilized through oxidation of pyron, yeah? So it occurs in cyclic forms of monosaccharides. We see this is tetrahydropyran, present now in D-ribopyranose. Also, we see this, the sugars we've learned this in biochemistry. Then, yeah, now we've completed heterocyclic rings. We can move to carboxylic acids and their derivatives. Yeah.
Na hiyo nini
Can you see my screen? Guys, can you see my screen?
Yes, Jasmila, we can see your screen clearly.
So aromatic compounds, yeah. The term originally was used to classify benzene and its derivatives only. And the term aromatic was used because of they used to have like a distinct smell. Like these compounds used to have a distinct smell, so they were classified as aromatic. And these compounds were found to be highly unsaturated and oddly enough, also very stable. Like, normally compounds that are unsaturated are known to be very unstable, but now for this category of compounds, they were found to be very stable. So instead, the term arene was used to describe aromatic hydrocarbons by the analogy. Yeah, arene was used to describe aromatic hydrocarbons. Similarly, with the way we say alkane, alkene, and alkyne. So yeah, a group derived by removal from alkane is called an alkyl group, therefore given the term R. So R usually stands for an alkyl group that is bonded now to the functional group, whatever functional group it is, yeah. So a group derived by removal of H from an arene becomes an aryl. So when we're dealing with the aliphatic carbons, we'll say an alkyl group is bonded maybe to a functional group. But then when we're dealing with these aromatic compounds, now it becomes an aryl group that is bonded to the functional group, yeah. Okay, so benzene is a common structure, very common in drugs. You can see it here in atorvastatin, sertraline, used for treatment of depression. We also have this Prevacid, a proton pump inhibitor, also in salmeterol, used in treatment of asthma. Yeah. So the structure came from, the structure was first, the idea of the structure was first brought about by this guy here. He's called Kekule. So this guy apparently had a dream, and his dream was simulating something of the sort. So this is how he decided on how the structure of a 6-membered ring would look like, a 6-membered fully unsaturated ring would look like, yeah. So Kekule proposed this in 1872, and the ring contains 3 double bonds that shift back and forth so rapidly that 2 forms cannot be separated. Like they keep shifting so bad, like so fast, sorry, here. So this is what is known as the Kekule structure. And you can see the shift. This is the shift that they're talking about. Benzene is best represented as a hybrid of 2 equivalent structures. It can be present as this structure, also as this. Normally we just put like a benzene ring and then we put a circle in between, and then yeah, but can be also present in both structures. So also these structures here, we have cyclobutadiene. They can also be present in different, in hybrids of equivalent structures, both this, and also this structure here, the 7-membered ring. So the concept of aromaticity, what classifies a compound, a heterocyclic compound, being aromatic or non-aromatic? So there are three important things that you need to consider so that we can say that either a compound is either aromatic or non-aromatic. So first, it needs to be planar, monocyclic, and also fully conjugated. And at the same time, it should be able to follow Haeckel's rule. Haeckel's rule says that the number of pi bonds should obey this rule. By pi bonds, we mean these pi bonds. We know every double bond contains has 2 pi bonds. So let's say benzene here, we know it has 6. So benzene obeys the Haeckel's rule. 2 pi bonds. Are we okay, guys? Should I continue?
Continue, Jasmila. Yeah, Haeckel's rule. Well,
Yes.
we are not in down things.
So benzene is not the only compound that exhibits aromatic stabilization. A compound can be aromatic if it satisfies 2 criteria. So the compound must contain a ring comprised of continuously overlapping pi bonds, continuously overlapping. By continuous, we mean, you see, this is not continuous because you see here we have pi bonds, here we do not have pi bonds. I think these are sigma bonds, and then again pi bonds. So for a compound to be specified as aromatic, it must have like continuous overlapping p orbitals, and then the number of pi electrons in the ring must be a Haeckel's number. By Haeckel's number, we mean it must obey this electronic rule, this pi bond electronic rule of 4n plus 2, where n is a positive integer. Okay, so compounds that satisfy the first criterion but have 4n electrons rather than 4n plus 2 are anti-aromatic. Example is this cyclobutadiene. We see that this does not obey the Haeckel's rule because it does not obey this formula here. Like if we were to put, instead of it obeying 4n plus 2, we see it's like if we put, if we multiply, how do I say this? If we put 1 here, it's going to be 4. So it's anti-aromatic. I don't know if I'm explaining it properly. But yeah, so it must obey the Haeckel's rule. Okay, so these are examples of polycyclic. Yesterday we said polycyclic aromatic compounds are compounds that have more than 1 heterocyclic ring. Example, this naphthalene, anthracene, and even this one. So you see all of these still obey they're still aromatic because, as you can see, they have the overlapping pi bonds and then the continued like pi electrons after, like with the double bonds. Yeah, so then heterocyclic aromatic compounds.
Benzene is a
bonds.
So is the benzene.
How is the benzene?
Like the benzene on a double bonds all around.
Yeah, now you see. So you see here there's like continuous, there's the continuous, what's the term I'm looking for? Continuous, yes, there's continuous conjugation. Yeah, continuous conjugation. So you see, let's say if we had a double bond here, and then we didn't have a double bond here, this compound wouldn't be aromatic.
Explain that in the simplest way possible.
Let me explain to him. Heterocyclic aromatic compound. So aromatic character is not limited to only hydrocarbons. It can also be found, this is the usual. So heterocyclic molecules aside, okay, I think we did this yesterday. Yeah, we did most of these yesterday. So we can pick from here. Nomenclature of benzene derivatives. I believe all of us are familiar with benzene as a structure as of now, so we can continue to its derivatives. So these are some of the common benzene derivatives that everyone must know. So we have, when the substituents is a methyl group, it's known as toluene. When the substituent is an OH group, it's known as phenol. Then anisole, when it has this ether substituent. Then aniline, when it has an amide. Yeah, and then when it has COOH, becomes a benzoic acid. Then this is an aldehyde derivative. Acetaminophen. Okay, this is a ketone when it is bonded to a ketone, and then also to the double bond. And there's this. So these are some of the few derivatives that everyone must know, at least offhand. So nomenclature of benzene derivatives for disubstituted benzene derivatives. So when two substituents occur on a benzene ring, 3 constitutional isomers are possible. So the substituents may be located by numbering the atoms as either ortho, meta, para. So when the substituents are located between carbon 1 and 2, it's a ortho. When it's 1 and 3, meta. Then 1 and 4 is para. This is an example. So let's say our counting starts here. So this is where the counting starts, the numbering. So 1, 2, 3. So 1, 3 dinitro, because we have 2 nitro groups, benzene, 1, 3 dinitro, benzene. Also the position is meta position. So we can also say M as in standing for meta, dinitro, benzene. Also, when the position is ortho, we can go for 1 bromo, 2 nitrobenzene, or we can say ortho, bromo, where bromo is like the location we see it's in the ortho position, ortho, bromo, nitrobenzene, and similarly to this structure over here. When the 2 substituents on the ring impart a special name to the compound, for example, toluene, cumene, phenol, and aniline, the compound is named as a derivative of the parent molecule. Let's say here, now the parent molecule is toluene because of the CH3. So we can say if our counting starts here, so 1, 2, 3, 4, so 4 bromo toluene. Similarly here, we see the parent molecule is aniline, so 1, 2, 3, so 3 chloroaniline, where we see it's also located in the meta position, so we can say M chloroaniline, and similarly here with the benzoic acid and xylene as well. For polysubstituted derivatives, polysubstituted derivatives like contain more than 2 substituents. So example here we see there are 3 substituents. So the parent molecule is toluene. So our counting starts from where the CH3 is 1, 2, 3, 4. So where chloro is, so we start with 4 chloro. 4 chloro, 2 nitro, toluene, and toluene because we are naming it according to this parent molecule. Similarly to this compound here, the parent molecule is phenol because of this OH group here. So counting starts here 1, 2, 3, 4, 5, 6. So 2, 4, 6 tri, because there are three bromo substituents, 2,4,6 tribromophenol, and similarly for this compound here. So now we are moving to we are done with benzenes. Now we are moving to these other compounds. Then finally, we are going to do carboxylic acid derivatives, and then that would be it, yeah. So alkyl halides, yeah. Alkyl halides are compounds containing a halogen atom covalently bonded to an sp3 hybridized carbon atom. So the name that is given to them is alkyl halide. Normally, users, we can find alkyl halides in laboratory and industrial solvents, example chloroform, also in dichloromethane. Then also invaluable building blocks for organic synthesis because of the variety of ways in which halogens may be substituted with other groups or eliminated to produce pi bonds. The general symbol for haloalkane is Rx, where R is the alkyl group and then X is the halogen. So X can be either fluorine, can be fluorine, can be chlorine, bromine, or even iodine. So if the halogen is bonded to a double bonded carbon, like the alkene, now the name changes to a it becomes a haloalkene, because now it's no longer bonded to an sp3 hybridized carbon, so it becomes haloalkene in the sense, in the position where it's bonded to like a double bond carbon. Then if it's bonded to a benzene ring, now it becomes a haloarine, because now it's bonded to benzene. Now the symbol will be ARX, where AR is the, it could be a benzene ring, it could be any arene, actually, yeah. So a haloalkane would look like this, where R is the alkyl group, so an alkyl halide. If it's bonded to a double bond, it becomes a haloalkene, yeah. And then if it's bonded to an arene, it becomes a haloarine or an aryl halide, yeah. Okay. Then also position of okay, alkyl halides are classified as either primary, secondary, or tertiary based on the number of alkyl groups it's connected to. If it's only connected to one alkyl group, we say it's primary. It's a primary haloalkene, alkyl halide, sorry. If it's bonded to two alkyl groups, it becomes a secondary alkyl halide. Then if it's bonded to three, it becomes a tertiary alkyl halide. So depending on the number of alkyl groups it's bonded to, so it can be primary, secondary, and even tertiary. So how do we name these alkyl halides? So the first thing, we need to identify the name of the parent molecule. Then we identify and name the substituents that are there. Then we number the parent chain and assign a locant to each substituent. And finally assemble the substituents alphabetically. So the same exact four-step procedure is used to name compounds that contain halogens. So the halogens, depending on the atom that is bonded to the alkyl group, it will give the suffix fluoro, chloro, bromo, and iodo. If it's fluorine, then it becomes fluoro. If it's chlorine, it becomes chloro. If it's bromine, then bromo, and similarly to iodine, it becomes iodo. Okay, so let's take an example here. The first thing, we need to identify the parent chain. So from counting, if we start our counting here, 1, 2, 3. So this is the parent chain. We know it's a propane. 1, 2, 3, prop, meth, eth, prop, so propane. Then we identify where our substituent is. Our substituent is in carbon number 2, so 2-chloropropane. Similarly, when we have this chain here, we first identify the parent chain, which is the longest chain. So 1, 2, 3, 4, 5. So 5, we know for alkyl compounds with 5 carbons, pentane. Then the location of our halogen atom, we see it's in carbon number 2. So 2 bromo, 2 methyl because of this. We didn't count from here because it would be shorter. 1, 2, 3. Okay. Okay, so it can either be, actually, if we count from either here or here, whichever it is we count from, we still see that methyl will still be on carbon number 2 and similarly to bromine. So let's say we start counting from here. So 1, 2, 3, 4, 5 pentane, then 2 bromo because of the location, carbon number 2. Also, the methyl group is in carbon number 2. So here. It would so let's say we have a double bond here. So now instead of it being pentane, it becomes pentene. And let's say we've said our double bond, let's say our double bond is here. So it's going to be on carbon number 3. So instead of pentane, it's going to be pent 3 -3 in. Yeah, so it just in the scenario where we have like a double bond, now it will become, yeah, the way Patrick is trying to write here. So pent, yes, pent 3 in. Okay. So another thing that we need to note, alkyl substituents and halogen substituents have similar priorities. So here, when we are naming, we are not going to count at saying we want to give bromine the smallest number. We start counting, looking where we will have the longest chain. Yeah, alkyl substituents and halogen substituents both have the same priorities. So this is the way to count, not this way. So our counting will start here: 1, 2, 3, 4, 5, 6, 7, not the way it's seen here. So alkyl substituents and halogen substituents both have similar priorities. So we are going to start on alcohols from here. Alcohols, okay, so we are familiar with ethanols, methanols. Methanol is what is present in the normal alcohol that we drink. So ethanol, practical. Ethanol is oxidized in our bodies twice. So the first time it's oxidized using alcohol dehydrogenase to give acetaldehyde, then the second time to give acetic acid. So in the body, acetic acid has functions, like it can be used for a variety of functions, but acetaldehyde does not have many functions in the body. And once there's a large amount of acetaldehyde, that is when you hear someone complaining of a hangover, the way Patrick will be complaining tomorrow.
Hey, Patrick manze, punguza.
Hey, we bwana unaongea hivyo na uko na captain kwa lab coat. Relax bro.
Our friend is clearly already intoxicated.
Okay, so we have methanol. Methanol is, if you've had this, I don't know if you've heard of this alcohol like Chang'aa. Yes, methanol is found in those alcohols. Methanol is found in changa. Now, methanol is even, oxidation of methanol is more poisonous than that of ethanol. So, methanol is oxidized to form formaldehyde. Then from formaldehyde, again, it will be oxidized to form formic acid. Now, formic acid is very toxic, even in small quantities, and a buildup is what causes blindness. If you've heard these, what are they called?
Illicit brews.
Yes, the illicit brews. Yeah, if you've had people going blind from drinking illicit brew, is because of formic acid. Yeah. So how to avoid a hangover? Dehydration is what normally also causes very bad hangover. So make sure you drink water as you're drinking. So you take a shot, you also drink water. Don't just take shots. The only way to also avoid is to take low concentrations of alcohol, so that even when the body is oxidizing the alcohol, there'll be low amounts of acetaldehyde. Yeah. And then finally, drink responsibly. Drink in small quantities over a long time together with water. Alcohols are compounds that possess the hydroxyl group, the OH, and the names are normally characterized by all, like methanol, ethanol. Yeah. So some of the naturally occurring ones are like this: beta D glucopyranols, cholesterol, and also cholecalciferol. So whenever you see oil at the end of a term, you just know that that is an alcohol. The nomenclature, so we'd say first, just like the way we named the alkyl halides, first you need to identify the parent name, the parent molecule, then identify and name the substituents, and then you assign a locant to each substituent, that is the number of the carbon in which the substituent is found. Then finally assemble the substituents alphabetically. Additional rules when naming, we replace the suffix E with all. Let's say we have methane will become methanol, ethane will become ethanol. So we see here, this is a hexane. So once there's an OH group bonded to the alkyl group, it becomes hexanol. Then when choosing the parent of an alcohol, identify the longest chain that includes the carbon atom connected to the hydroxyl group. So now we want the longest chain that is bonded towards the alcohol. So we won't count going this way. We are going to count following where the OH group is. Let's say if our OH group was here, we would have been counting going towards this end. But now our OH group is here. So now our counting is also going to follow this sequence. So 1, 2, 3, 4, 5, 6 hexanol. And then we have 1, 2, 3, 4. So 1, 2, 3, 4, 5. So we'll say 5 butyl hexanol in this case. And then when numbering the parent chain of an alcohol, the hydroxyl should receive the lowest number. Unlike when we were naming the halide, we say that the halides and the alkyl, they have the same priority, but here we want to give our OH group the lowest number. Yeah. So despite, okay, even if let's say in a structure we have pi bonds, you see here we have pi bonds, we have halogens, we have this halogen here, we also have the OH. So priority starts we want our OH to have the lowest number. So we start our counting from here so that we can give OH the lowest number. So 1, 2, 3, 4, 5, 6, 7. So yeah, we want our OH group to have the lowest number. Then cyclic alcohols, these are cyclic compounds, non-aromatic, cyclic compounds that are bonded to OH. So example, this is a 6-membered ring, cyclohexanol, hex because it's a 6-membered ring. So here disubstituted, we see a methyl group and we also see an OH group. So counting starts here. As usual, we want to give our OH group the lowest number. So 1, 2, 3. So 3-methyl cyclohexanol. And then we come to phenol. Phenol is a benzene ring containing OH as the substituent. So this is what phenol looks like. Phenol, we can see it's found in THC, tetrahydrocannabinol, in weed, then also in dopamine, the neurotransmitter. We know that deficiency of dopamine is what causes Parkinson's disease. Diols, these are compounds that contain two OH groups. They can even contain more. That's what these are what are known as polyols. Diols contain two OH groups. Polyols contain more than two OH groups. So we see here, this has two, 1, 2. So 1, 2 ethane, E-diol, and then we see compounds like this that have more than two OH groups. So 1, 2, 3, because in carbon 1, carbon 2, and carbon 3. So 1, 2, 3 propan, E-triol, tri, because we have 3 OH groups. Yeah. Then another group is ethers. Ethers are compounds that contain oxygen, an oxygen atom bonded to two R groups. Yeah, where each R group can be an alkyl, aryl, vinyl group. Example here, we see this side, this is an oxygen. On one side, it's bonded to an alkyl group. On this other side, it's bonded to this side aryl group, this side alkyl group. So these are ethers. Ethers, oxygen bonded to two different to R groups. It can be alkyl and alkyl. It can be aryl and aryl, vinyl, alkyl. So whenever you see an oxygen bonded to those two, we know they are ethers. So naming of ethers, we select the longest carbon chain as the parent alkane. So there are two ways of naming these ethers. I'm going to show you. So the first one is this one, where we select the longest carbon chain as the parent alkane and naming the OR group bonded to the alkoxy group. So for example, this we choose, let's say this side we have an ethyl group. On this side, we have a pentyl group, because here 2 carbons, then 5. So the naming is we are going to name according to the longest chain, which is the pentane in this case. And then for the short chain, we are going to add oxy. So if this, let's say, would have been a propane, it would have been prop-oxy. But since it's ethyl, it becomes ethoxy. So ethoxy pentane. This is one way we can name ethers. Yeah. And then in another way that we can name ethers, we can name them alphabetically, where let's say, okay, for here we have ethyl on one side and then methyl on the other side. So it becomes ethyl, methyl, ether. So we name them alphabetically, where you see we started with E, then M. Then for this one, butyl, so it becomes tet-butyl. Okay, for this one, this is an exception. We don't say methyl tet-butyl. No, we follow this butyl here. Like we consider this butyl here. So it becomes tet-butyl ether. So these are examples of unsymmetrical ethers. Symmetrical ethers are, let's say this side we have ethyl and ethyl, that would be a symmetrical ether. But so these are all unsymmetrical ethers. Yes, then we also have cyclic ethers. These ones have special names. The presence of an oxygen atom in a saturated ring is indicated by the prefix ox, prefix ox, and the ring size from 3 to 6 are indicated by ending with irane, ethane, olane, and ane, respectively. So we see for this 3-membered ring here, it becomes oxyrane. Oxyrane because of this oxygen, irane because it's a 3-membered saturated ring, the same thing that I was talking about yesterday. Then for a 4-membered ring, oxyethane, ethane because it's a 4-membered saturated ring, similar with 5-membered, 6-membered. But we see now we have these compounds that already have common names like this, or it's known as tetrahydrofuran. Then when it's a 6-membered ring, tetrahydropyran. All of these are names that can be used. All of these names are correct. We can use both of them to name these compounds. Yeah. And then we have oxyranes, oxyranes are these 3-membered rings. So yeah. So oxiranes, these are more reactive than other ethers because of the significant ring strain. If you remember yesterday, I had told you the smaller rings have more ring strain in comparison to the bigger rings. So you see this one has so much strain. So they are very reactive. These compounds are very reactive. So you see this is the oxirane. And then, yes. Yeah, literally that's it. You just need to know that the smaller the ring, the more ring strain it has and the more reactive it becomes. When we are moving now to these rings with higher numbers, 4, 5, 6 now, they become less reactive because they don't have very much ring strain. Then nomenclature, this is okay. Now this is another way of naming oxiranes. Yeah, there were 2 ways, but the first method was a bit complicated, so I just chose to take this. So the parent is considered to be an oxirane ring. So whenever you see an oxirane ring, this is the parent. This is the parent ring. So any substituents that are bonded will be named according to the numbering. So you see the numbering starts with the oxygen, then 1, 2, 3. So we see there's 2 ethyl groups bonded in carbon number 2, and then 2 methyl groups bonded to carbon number 3. So it becomes 2,2-diethyl because of these 2, then 3,3-dimethyl because of the 2 methyl substituents that are bonded to carbon number 3 here. So it becomes 2,2-dimethyl, 3,3-diethyl, 3,3-dimethyl oxirane. Yeah. Then there are these other ethers known as crown ethers. These are cyclic polyethers, and they're known as crown because of, you can even see how they look like because of their molecular models. They resemble crowns. So these crowns are named, we count the number of carbons. So let's take this. Let's say we start our counting from here. 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So 12, this is where the 12 comes from. Crown 4, because we see like the structure. So similarly to these other ones, wherever it is that you will start, you can start counting from any of the oxygens. Yeah. Amines. Amines are derivatives of ammonia in which one or more hydrogens are replaced by alkyl or aryl groups. The amines are classified as primary, secondary, and tertiary. We say primary depending on the number of alkyl groups that are bonded to that nitrogen. You see, if it's just 1, it becomes primary. If it's 2, secondary, and 3, tertiary. Then we have heterocyclic amines, an amine in which the nitrogen atom is part of a ring is classified as heterocyclic amine. When the nitrogen is part of an aromatic ring, the amine is classified as heterocyclic aromatic amine. Yeah, as seen here. The nitrogen is part of the ring, so yeah, nitrogen is part of the ring for all of these structures. So all of these are heterocyclic amines, yeah. Then I think we also did some of these yesterday. Quinoline, you can see this structure, quinoline present in, found in mefloquine, and then, yeah, we did most of these yesterday, so. And ammonium salts. So normally a normal amine, let's say an NH group, when it's bonded to, let's say benzene, it's known as aniline. When it's present in when it's present as part of the ring structure, pyridine for a 6-membered ring. But now when it's replaced by ammonium, it changes to become an anilinium for aniline, pyridinium for pyridine, and so on. Now it has become an ion. It's no longer a salt. So an ion containing a nitrogen atom bonded to any combination of 4 alkyl or aryl groups is classified as quaternary. Quaternary, that means there are 4 alkyl groups, or 4 alkyl, no, not 4 alkyl groups. An ion containing a nitrogen atom bonded to any combination of 4 alkyl or aryl groups is classified as quaternary, or 4 degrees. Ammonium ion. So compounds containing such ions have properties similar to those of salts. Then the last part, carboxylic acids. So carboxylic acids are compounds that contain the COOH group. The functional group of carboxylic acid is the carboxyl group, and the name is made up of the carbonyl group. This is the carbonyl group is C double bond O, and a hydroxyl group, the OH. So together is what make like when you have a carbonyl group and the hydroxyl group together is what makes the carboxylic acid group. Yeah, I don't know if I'm making sense.
You are.
The general formula for okay, thank you. The general formula for an aliphatic carboxylic acid is normally RCOOH, where R is the alkyl group. Then the general formula for an aromatic carboxylic acid is ArCOOH, where AR is the a ring. It can be a benzene ring. It can be literally, it can be any any aromatic ring. Carboxylic acids that are present in pharmaceuticals. We have acetylsalicylic acid, which is aspirin. Aspirin is used, it's an analgesic. Then we have 4-amino salicylic acid used in treatment of TB. I think this one is pyrazinamide, the pyrazinamide. Then isotretinoin, vitamin A, used in treatment of acne. Then naming of the carboxylic acids, we have the monocarboxylic acids, where, so naming, we have to, there are two. Okay, in naming, these compounds containing one carboxylic acid group are named using the suffix oic acid. Carboxylic acids have the highest priority in all of the functional groups. So in comparison to all of the functional groups that we'll have come across, carboxylic acids tend to have the highest priority. So let's say even if in a molecule like this, we have the COOH and maybe we have NH2 here, we are going to name this compound based on the as a carboxylic acid. We are not going to name it as an amide because carboxylic acids have the highest priority. So the naming, the parent is the longest chain that includes the carbon atom of the carboxylic acid group, which in this case is here. The carboxyl carbon atom is always assigned number 1. So this carbon here, the one with the carboxylic acid, this is the first carbon. We are not going to start naming from here. We're going to start naming from here. So 1, 2, 3, 4, 5. So 5 hydroxy because of this OH group. Then we have these 2 methyl groups bonded here. So 4,4-dimethyl. Pentanoic acid because we've seen that the parent chain is a pentane, a 5-membered chain. So, and then these are some of the common monocarboxylic acids. Monocarboxylic acid because they only have one COOH. group. If they have two, then it becomes a dicarboxylic acid, but these are some of the common monocarboxylic acids. We have formic acid with only one carbon. When it's two carbon, this could have been also ethanoic acid. This is methanoic acid, ethanoic acid, propionic acid, and yeah, similarly to these other ones, and also this that is bonded to this arene here, the benzene. So this is benzoic acid. And then diacids, these are compounds that contain two carboxylic acid groups. Now, instead, now the suffix goes, the suffix goes from oic acid to dioic. So example, this, we can start counting from any side because you see both of them have the same, they have the same priority. So 1, 2, 3, 4, 5. If we start from this side, 1, 2, 3, 4, 5. So pentane dioic acid. And then for this compound here, 1, 2, 3 carbons. So propane dioic acid. Propane dioic acid. Yeah. So acidity of carboxylic acids, when carboxylic acids are treated with salts, with a base, with a strong base, example sodium hydroxide, we see it forms a salt, yeah. And these salts are very water soluble. They are ionic and also very water soluble. So carboxylic acids, once they react with bases, they form salts. This is an example. So, then once a carboxylic acid reacts with the base, it goes from, now the suffix goes from ic acid, we are going to add this suffix instead, ate, because now it has become a salt. So from benzoic acid, it becomes sodium benzoate because it has reacted with this sodium hydroxide. Yeah? Then we see it gives the salt and water. Similar with this one, ethanoic acid or acetic acid, when it reacts with potassium hydroxide, it gives potassium ethanoate, or you can also say acetate. Whenever you see acet, you know acet means like a two alkyl. I think I'm making sense. Yeah, it's like acetic acid. Acetic acid is also ethanoic acid. Ethanoic acid because it has two carbons. Yeah, you understand? Right. When we compare the carboxylic acids to the inorganic acids are like hydrochloric acid, sulfuric acids. We see that carboxylic acids are extremely weak acids. So when compared to most classes of organic compounds such as alcohol, they are relatively acidic. Like in comparison to the inorganic acids, they are weak, but once we compare them to now these other organic compounds such as alcohol, they are more acidic. So carboxylic acids are more acidic than alcohols. Then we have aldehydes and ketones. So aldehydes and ketones are similar in structure. Both classes possess the this carbonyl group. We see this is the carbonyl group, the C, or the C double bond O, C double bond O. We see in aldehyde, one side is bonded to an alkyl group, then the other side we have a hydrogen. But in ketones, both sides are bonded to either alkyl, can be alkyl, or arene, aryl, yeah. The carbonyl of an aldehyde is flanked by a hydrogen atom, and a carbon atom, while the carbonyl group of a ketone is flanked by two carbon atoms. You see, we'll have a carbon here, but in aldehyde, we'll have a carbon here, and this side is flanked by a hydrogen. So these are examples of ketones. We see ketone is present in this hormone progesterone, and then also testosterone in both. Then nomenclature of the aldehydes. When numbering the parent chain of an aldehyde, the aldehydic carbon is assigned number 1. So this is the aldehyde carbon here. This is the number. This is what we give our number 1. So again, we see here that this carbonyl of the aldehyde has more priority than a hydroxyl group. So numbering will always start from this carbonyl group here. So 1, 2, 3, 4, 5, 6, 7. We want the longest parent chain. So we see in carbon number 5, we have OH, so 5 hydroxyl, 5, 6 dimethyl, 5, we see 1 methyl group is here in carbon number 5, then the other is in carbon number 6, so 5, 6 dimethyl, 6 heptanol. We see it's not A because we have this double bond here. Yeah. So yeah, 6 hepti. Yeah, we follow the alphabet. Then my laptop in your hand. Okay. Then a cyclic compound containing aldehyde group immediately becomes it becomes now a carbaldehyde. When a cyclic compound is bonded to the aldehyde group, it's called a carbaldehyde. So example, we have this cyclohexane and bonded to this to the aldehyde group, it becomes cyclohexane carbaldehyde. Whenever a cyclic compound is bonded to an aldehyde, this is the name that we are going to use. Similarly here, this 5-membered ring, so a cyclopentane carbaldehyde because of the aldehyde. Then preparation of aldehydes through okay, so there's ozonolysis of alkenes. So alkenes in the presence of ozone and DMS, which is dimethyl sulfide, will give us an aldehyde. Yeah, we see these 2 aldehydes, yeah. So this is one way of preparing aldehydes through ozonolysis of alkenes. So alkenes in the presence of ozone and dimethyl sulfide will give us an aldehyde. Then now we come to ketones. Similar to the way we were naming aldehydes. So first thing, we identify the parent, then we identify and name the substituents, whatever substituents will be there apart from the carbonyl substituent, and then we assign the numbers, then finally assemble the substituents alphabetically. Yeah. So so let's say we have this butane here. So once there's a ketone group, the E is replaced by the suffix ONE, 1 or 1. So 1, 2, 3, 4, but, so butanone. So the position of ketone group is indicated using a locant. So let's say in this long chain here, we start counting from here. So 1, 2, 3, 4, 5, 6, 7. So unlike the aldehydes where we say that the carbon on the aldehyde, on the carbonyl group of the aldehyde will be the first. We see now there's an alkyl group on this side, an alkyl group on this side. So we cannot start counting from the middle. We start counting from this side, but we want our ketone group to have the lowest number. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. How? Yeah. So 1, 2, 3, 3 heptanone. Then preparation of ketones is through oxidation of secondary alcohols. So this is our secondary alcohol in the presence of sodium. Okay, can someone help me? What is this compound? Sodium chromate.
Yeah, sodium dichromate.
Yeah.
Dichromate, yeah.
So in the presence of sodium dichromate and sulfuric acid, also water, it will give us a ketone. Then another method is through also ozonolysis of tetrasubstituted alkenes. Unlike here, you see, we were just, we didn't have, well, this is more of a disubstituted alkene. We see it's even a cis alkene. Now, when we want to prepare a ketone, we should have a tetrasubstituted alkene. So in the presence of ozone and dimethyl sulfide, it will give us a ketone. Then also another method is through Friedel-Crafts acylation. So we start with benzene, then acylation using an acyl halide. It will give us a ketone, but this is more. This is an acyl. I'll explain to you later. So benzene, and then we use this acyl benzene, and then in the presence of this acyl halide and aluminum chloride, yes, will give us a ketone. Yeah. And then finally, preparation of carboxylic acids. So preparation starts from, we use an alkyne. So oxidative cleavage of an alkyne. So we start with an alkyne in the presence of ozone and water will give us a carboxylic acid. Yeah. And then also we can see here hydrolysis of nitriles like this. The presence of this ion and heat will also give us carboxylic acid. Then oxidation of also primary alcohols in the presence of sodium dichromate and sulfuric acid and water will give us also carboxylic acids. Also oxidation of alkyl benzene. Nimemaliza shot yangu. Oxidation of alkyl benzene. The oxidation of alkyl benzene in the presence of this will also give us an alkyl. I mean, it will give us this carboxylic acid, the benzoic acid. Then reaction, these are some of the reactions that carboxylic acids undergo. We see carboxylic acids are reduced to alcohol upon treatment with lithium aluminum hydride, and then it produces an alcohol. Then an alternative method also is reducing carboxylic acids using borane. Borane, and then it also gives us an alcohol. So reduction of carboxylic acids will give alcohol, yeah, and these are primary alcohols. Then borane reacts selectively with carboxylic acid groups in the presence of another carbonyl group, so reaction of these carboxylic acids will give this. Okay, so I think we are done with everything. Yeah, these we already did. Yeah, these we've already done this, even the naming. Okay, nomenclature of acid halides. So when acid halides when an acid halide group is connected to a ring, the suffix carboxylic acid is replaced with carbonyl halide. So yeah, so the carboxylic acid is this carboxylic acid now becomes a carbonyl halide. Then nomenclature of acid anhydrides. Acid anhydrides are derivatives of carboxylic acids that are it's like having two carboxylic acids bonded together. So they form an acid anhydride. Let's say we have two acetic acids, it will form acetic anhydride. It's like having two carboxylic acids bonded together, yeah? So acetic anhydride here, this succinic acid, when we have two when we have two I don't know what am I trying to say, when we Yeah, when we have 3 carbons. Is it 3? Wait,
It's 4.
it's 4. Yeah, so it becomes succinic acid. So naming of the acid anhydrides. Unsymmetrical anhydrides are named by indicating both acids alphabetically followed by the suffix anhydride. Let's say there was supposed to be another benzene here. No, there's no another benzene, sorry. You see on one side we have this, it was acetic acid, then on this other side it was benzoic acid. So we see acetic, benzoic, anhydride, like one acid, the other acid, and then anhydride. But now we follow the alphabetic order. Yeah. Then preparation of acid anhydrides, they can be prepared. Carboxylic acids can be converted to acid anhydrides with excessive heating. So excessive heating of a carboxylic acids will produce an acid anhydride. So let's say here we have acetic anhydride because we see this was acetic, excuse me, acetic acid. It was heated up and then it became acetic anhydride, and also it produces water. So this method, okay, now for this method of preparing acid anhydrides is only practical for acetic acids. Most other acids cannot survive excessive heat. So this method of preparing acid anhydrides can only be used with acetic acid. Then another method, an alternative method for preparing acid anhydrides involves treating acid chloride. This, you see, this is a acid chloride with a carboxylate ion. This is a carboxylate ion, and then it will give us the acidic anhydride, and also depending on the ion that you'll use here is what will determine this product here. So for this case, because we use the sodium carboxylate ion, that's why we have sodium chloride. And also the halide, whatever halide will be here, but mostly I think they just use chloride. So acid chloride in the reacting with this carboxylate ion will give us an acid anhydride. Then another method is through reaction of acid, the reaction of anhydrides are directly analogous to the reaction of acid chlorides. So the only difference is the identity of the leaving group. So you see this acid chloride, this chloride will be replaced and then will be replaced by another with this group. I don't know how to explain this, but yeah, the chloride is the leaving group. So the chloride will leave. Yes, and then the oxygen from the other acid will bond and form the acid anhydride. Acetic anhydride is often used to acetylate an alcohol or an amine. So this is the alcohol. We see acid anhydrides are mostly used to acetylate alcohols to form esters. So for amines, acetylation of amine will produce an amide. Then esters. So esters are named by first indicating the alkyl groups. I think we've done this. Have we done esters? No, we've only done ethers. So esters are named by first indicating the alkyl group attached to the oxygen atom, followed by the carboxylic acid, for which the suffix -ic is replaced by -ate. So we see, like in acetic acid, now we remove this suffix here, -ic acid to -ate. So this is ethyl acetate. Then similarly here, it's the same. Then we have these cyclic esters. As usual, we always name according to the we follow this, then depending on the number of carbons on this this cyclic with this cyclic compound. So here we see it's a 6-membered carbon, so cyclohexane carboxylic acid. Yeah. Preparation of esters. So preparation of esters can be done through SN2 reactions. When reacted with a strong base, this is a carboxylic acid, when it's reacted with a strong base,